We'll now discuss the concept of metastability and how we can use synchronizers to reduce its probability. So what we've seen, according to the timing parameters of a flip-flop, if you have a clock and an active edge of the clock is a positive, you should keep the input D stable around that clock with setup time and a hold time. So what I'm showing you here is actually the aperture window. So in case 1, for example, let's assume that D stabilized or was set to 1 for the whole period of the aperture. So I would expect Q, the output, to reflect that input 1. And after the active edge of the clock that is here, after a certain period of time, let's say contamination or propagation, I expect Q to be 1, at least till the next active edge of the clock. So from clock to Q, that's the delay you see in here. There's a little bit of a delay, and that's clock to Q. The same goes for when D is stabilized at 0. So let's, in case 2, I have D that is stable at 0. I would expect whatever Q is, whether it's 1 or 0, I know after the active edge of the clock that is here, after a certain period of time, I know for sure Q will be 0 onward. And this is why we sometimes refer to flip-flops as bistable devices, because they usually are stable at 0 or stable at 1. They give me a stable output of 0 or 1. Now, the interesting question is the following. What if I violate this aperture window here, whether it's the setup time or the hold time? Meaning, what if I actually change D from 0 to 1 or 1 to 0? I'm changing D within that aperture. What happens? Well, as it turns out, metastability happens. So the flip-flop will be in a metastable condition. What does that mean? Well, here's a diagram in here that shows me a metastable condition. This diagram is actually for a single flip-flop, and we kept violating its timing constraint, whether it's setup or the whole time, over and over again, and we're just superimposing the Q on top of like all these trials, and that's what we see in here. So this one here, I'm just going to indicate this is actually logic 1 and this is logic 0, and this is where the change happens. So like after the clock edge, the active edge of the clock happens in here, what we see is the output of that flip-flop goes to what we call a metastable state, and the metastable state is actually neither 0 nor 1. It's actually neither of these two values, neither 1 or 0. It's actually, if you think about it, 1 or 0 are associated with some sort of a voltage, depending on the technology we're using, whether it's 5 volts, 3 volts, or 1.8 volt, doesn't matter. What matters is the following. It's actually in the forbidden region. It's in the region where it's neither 0 nor 1. And that's why we call this a metastable condition. So violating this timing constraints or the timing parameters of the flip-flop will result in that. But because flip-flops are bistable devices, eventually they will stabilize to 1 or 0, and this is what this diagram is showing me. So it's showing me actually a couple of things. It's showing me that, yes, if you violate the timing constraints, whether it's setup or hold time, you will stay in a bistable or a metastable condition or metastable state, and eventually you will go to 1 or 0. And actually, that's a random variable. We do not know whether it's 1 or 0. So for example, take a look at this diagram. D went from 0 to 1. The output Q here is basically unknown. It's a random variable that takes a value 0 or 1. And I don't know what it is. And the time it takes from the active edge of the clock or the change till you reach that 0 or 1, what I'm seeing in here is it might reach it early or it might reach it really late in here. So that time, as it turns out, is what we call a resolution time. So it's the time that it takes to resolute to a stable condition of 0 or 1 is also a random variable. And theoretical and actually experimental analysis came up, like in this topic, it's actually really heavily studied, but they came up with, the researchers came up with this number, and this number is actually that gives me the probability that the resolution time will be like after a certain period of time. So what we see from here is the following. We see that while T0 is and tau are related to the flip-flop here, the parameters that setup time the whole time, and TC is actually the clock period, the system clock period. But this isn't what's important. What's important is the following. It's actually exponential. What does that mean? Well, it means that the probability actually goes all the way down. Like with time, it actually, the probability that it will take longer time gets reduced and reduced and reduced till it reaches 0. So what I'm saying in here is the probability that it will stay in a metastable condition, that it will not resolute, or it's not going to resolute to 1 or 0, goes like to 0 very, very quickly. It goes to 0 very quickly. That's what this equation tells me. So to summarize, a flip-flop is a bistable device that should stabilize at 0 or 1. If you violate its timing constraint or the timing parameters, or you change D within the aperture, you will get a couple of things. It's either a 0 or 1, and you don't know for how long it will take to reach that 0 and 1. All right, so this is not very good because it might create some errors if you have like a critical system and you're running critical systems and this happens. It will actually give you some unknown situation and your system will give you some erratic behavior. So it should be avoided. So you might be asking, but who cares? I'll just make sure that I actually not violate the setup time or the hold time. I'll just make sure that my system doesn't. And what I can tell you is the following. Usually what you do is you have a system that is external to the system you're designing and another one here, and that's your system. So this is your system here. And this is we call it external system. And the external system could be a completely digital logic design that runs on its own clock and everything, and your system has its own clock. So let's say that you operate at a clock 1, and this one here might not even operate at a clock. Maybe it doesn't need a clock. Maybe it's just a button, like a push button or something like that. So if you do connect that particular one to that system directly, you might get that metastable condition because that system will output, or the output you get from here might change at any moment it wants. It doesn't know the internal clock that you have here in your system. So the solution is to use what we call synchronizers. So what do synchronizers do? Well, synchronizers do the following. They take some sort of an external input to D, and they give me a highly stable output Q. And of course, it should take the clock of your system here. So your system is also connecting or providing that clock too. So what's the purpose of a synchronizer? Well, the purpose of the synchronizer takes a D and it doesn't care whether it's synchronized with the clock or not. And it gives me a Q that is highly likely stable. So the probability that it's in a metastable condition will be very, very small. It's still not 0. You might get a metastable condition or a metastable state, but generally speaking, synchronizers will give you something that is either 0 or 1. So if D happen to change within the aperture of that clock, you will see that Q will give you 0 or 1 because they're already resoluted internally. And that's what synchronizers are, and we usually use them to connect to systems or something like an asynchronous input to a synchronous system. So how do we build them? Well, as it turns out, it's really simple to build synchronizers. There's many ways, but this is one of the most common ones I've seen. So usually you can just do it with a couple of flip-flops cascaded with nothing else. You just take a flip-flop, you take another one, and you just cascade them. You connect the data to the first flip-flop, and you take the synchronous data or your Q actually from the second flip-flop, and this supposedly will give you like a highly stable output. Okay, so of course this will cause certain delays. Let's assume that that data was did not violate any timing constraint whatsoever. So it will take, like for example, you put a 1 in here, it will take 1 clock cycle for that one to appear in here, and another clock cycle for that one to be here. So it took you about 2 clock cycles to actually get from the input all the way to the output. Okay, so it causes a little bit of a delay, but I think it's worth it, especially if you're dealing with critical systems and you don't want it to go into an erratic behavior. So let me explain to you how the synchronizer actually works. So a synchronizer like this, so here I have a flip-flop F1 and I have another flip-flop F2. And I connected both of them to the same clock, and this is the external system will be connected in here, and my system will be connected to that, and supposedly this is always stable. So what happens if D happens to change outside or does not change within the aperture? So this will be stable. Whatever you put in here, let's assume you put 1 in here, it will appear in here, and eventually you'll get that 1 in here. The same goes in here. If you put a 0 in here, after 1 clock cycle, it will appear in here. After 2 clock cycles, this 0 will appear in here. Now, more interestingly is the following. If D changes within the aperture, so it will put this particular flip-flop in a metastable condition, and that's what I see in here. So D2 is the output of the first flip-flop, and it turns out that D changes within the aperture in here, so it will put that output in here in a metastable condition for a certain period of time. Hopefully that period of time is actually less than the total clock period available to me, and also less, or it's not only less than the clock period, it's also less than the setup time for the second one. What I'm saying in here is hopefully the resolution time or I'll get a stable condition in here, hopefully before the setup time of the next flip-flop. If I do, That means this signal will be stable for the setup time and hopefully for the whole time, and I will get it after propagation clock to Q, and I'll get like a highly stable 0 or 1. Even what I'm saying in here, even if D happened to create a metastable condition for F, it will eventually be stabilized, whether it's 0 or 1. What I care about is I will not get something in the forbidden region. I'll get something that is extremely stable. However, the stability is not guaranteed, and theoretical and experimental studies tells me that the probability that this is not metastable, or let's say the probability that is metastable, it's extremely, extremely small, but it's not zero. So if you really, really care about this, or this topic is really important for your system, what you can do is you can cascade another flip-flop in here, or another flip-flop as well. Of course, the more flip-flops you have, maybe this one will be metastable, and the time we have is not enough for this one to resolute, so this will be also metastable. So these two flip-flop, hopefully, before the signal reaches your system at this end, hopefully it will the signal eventually will be stabilized. Of course, adding extra flip-flop will add extra delays, so nothing comes for free. Yes, you will get like something that is highly stable at 0 or 1. However, you will need, like if the system was stable originally, you will need 1, 2, 3, and 4 clock cycles to get it.